In this video, I'm going to be showing you guys how to solve for definite integrals. Now, in order to solve for definite integrals, you need to know what the fundamental theorem of calculus is. I will do a quick review, and I'll show you guys the formula for it, but if you want a more in-depth explanation, a video link will be down in the description for my fundamental theorem of calculus video. So, basically what the fundamental theorem of calculus states is that if this capital F is your antiderivative, you can plug in the upper bound into your antiderivative, and subtract the lower bound plugged into your antiderivative. So basically, first thing you need to do when you solve for a definite integral is find the antiderivative. So what's the antiderivative of x squared? Well, the antiderivative of x squared is, using the reverse power rule, is x to the power of 3 over 3. Plus c, of course. But the thing about the fundamental theorem of calculus is that you can get rid of the plus c. The arbitrary constant is not necessary when you're solving for definite integrals. It wipes out away. And again, the video link down in the description will explain why that happens if you're curious. But right now, this is our antiderivative. So this is our capital F of x. So now that we have the antiderivative, what do? Well, per the fundamental theorem of calculus, we want to plug in the upper bound into the antiderivative. So the upper bound is 4. So 4 to the power 3 over 3 is your upper bound b plugged into your antiderivative x cubed over 3. And you subtract it from the lower bound. And yes, you must subtract from the lower bound every single time, even if it's 0. So the lower bound is 1 to the power 3 over 3. Now, I mean, like, most teachers would be fine with you leaving it in this form. Once you have it in some constant form, you're really going to be fine. Like, most teachers really don't care about that. But if your teacher is stingy and they want you to simplify, basically the simplification for this is 64 over 3 minus 1 over 3, and that's equal to 63 over 3, which is equal to 21. So your final answer for the definite integral of x squared from 1 to 4 is 21. So let's go ahead and first find the antiderivative for this. So the antiderivative for 2x plus 1 is equal to, well, using reverse power rule, x squared plus x. All right? If you have some constant, just multiply it by whatever you're integrating with respect to. And in this case, we're integrating with the respect to the variable x, hence the dx. So I just multiply x by 1 here, and since it's a constant, we can do this. And also this use reverse power rule as well. But basically, our antiderivative is x squared plus 1. So all we need to do is plug in the upper bound. So the upper bound is 16 squared plus 16. So this is for the upper bound, and we subtract it from the lower bound. And I'm going to do and put the lower bound every time, even if it's 0, just for consistency's sake. But most of the time, if you have something like this, like a non-trig or non-exponential function, you don't have to worry too much about the 0. But again, at your own discretion, of course. Eventually, you'll pick up a very good pattern recognition for that, though. But basically, what we have here is 16 squared plus 16. And 16 squared plus 16 is equal to 272. Now, yes, your bounds can have negative numbers in it, and you have to treat the negative numbers just like they're negative. So, first find the antiderivative. You always want to find the antiderivative first. And the antiderivative for your function is, using reverse power rule, you have x to the power 3 over 3 for this term. And then for this term, you have 3 over 2 x to the power of 2. And again, you could ignore the arbitrary constant. So this is your antiderivative, capital F of x. And then you want to plug in the upper bound, 1, into this. So you have 1 to the power 3 over 3 plus 3 over 2, 1 squared. And subtract it from the lower bound input. So you have negative 1. So negative 1 to the power of 3 over 3 plus 3 over 2 times negative 1 squared. All right, it's a little bit of algebra and arithmetic here, but let's go ahead and evaluate this. You get 1/3 plus 3 over 2 minus negative 1 over 3 plus 3 over 2. One thing about this negative is that it distributes into everything. So we get 1 over 3 plus 3 over 2 plus 1 over 3 minus 3 over 2. As you can tell, I distribute the negative into both of these terms. And what happens is that the 3 over 2 cancels, and all we get left off is 1 over 3 plus 1 over 3, which is just 2 over 3. Okay, so for trig functions, make sure you always plug in the 0, because for trig functions, a 0 can equal 1 or 0.72 something. Okay, so make sure you plug in the 0 for if you see a trig function in your integrand. But let's find the indefinite integral of this first. The integral of sine of x plus 2 is equal to negative cosine of x plus 2x. And this is equal to your antiderivative. Alright, now that we have this, we should plug in our upper bound and lower bounds. So your upper bound is pi. So if we plug in pi into this, we get negative cosine of pi plus 2 pi. And we subtract the lower bound antiderivative. So we get negative cosine of 0 plus 2 times 0, which is just 0, so we can ignore it. So we get left off with this. Well, if we evaluate cosine of pi, we get negative 1. And a negative 1 is just positive 1 plus 2 pi minus, well, since these minuses cancel out, we get plus cosine of 0, which is just 1. So our final answer is 2 plus 2 pi. So keep in mind the 0 actually had a value here. That's why if you didn't do that, then you would omit this plus 1. You would get 1 plus 2 pi, and your answer would be wrong. So make sure you plug in the 0 every single time until you get a good pattern recognition for it. So the thing about e to the x is that the integral of e to the x, or the antiderivative, is the same thing. So if we want to take the integral of this, we can factor out the 3, and we just get e to the x. So we get the integral of e to the x, which is e to the x times 3, which is equal to 3e to the x. So it's the same thing. So this is our antiderivative. All we need to do is plug in the upper bounds and the lower bounds for this. So the upper bound is 5. So if we plug in 5 into the antiderivative, we get 3 times e to the power of 5 minus the lower bound, 3 times e to the power of 0. So in total, our answer is e to the power of 5 minus 3. E to the power of 0 is just 1, so 3 times 1 is just 3. So, yep, remember, always plug in the 0. That was a lesson for you guys, in case you didn't do that. But let's move on to like one last problem. I think that should be enough. So you might be wondering how the hell will you solve this integral? Oh my god. Well, essentially, what we have here is a piecewise function. Yep, the absolute value function is a piecewise function. So what is this piecewise function? Well, this function is basically stating that any value less than 0, so when x is less than 0, use the function negative x. And when x is greater than 0, use the function x. Right? It just looks like this. The graph looks like this. And anything to the left of 0 or less than 0, you have the function negative x, which makes sense. This is just a straight line with the slope of negative 1. And anything past 0, you have a straight line with a slope of just 1. So what you can actually do to solve this integral is actually solve the integral of both of these functions. You can solve the antiderivatives of both of these functions, and then only apply the bounds of 3 and negative 3 for the functions that are applicable to those bounds. So what do I mean by this? Well, if we take the integral of just x, let's take the integral of x, we get x squared over 2. Now, if you want to solve for the integral of 3 to negative 3 for the absolute value of x, you can either just plug in 3 and then multiply by 2 since the function is symmetric, or you can solve for the integral from 0 to 3 for x, and then also solve from the integral of negative 3 to 0 for negative x. And you can add the two values together at the end, and as a result, you'll get the integral from negative 3 to 0 for your function. So you can actually add integrals together by separating their bounds. The logic works out. The area all works out. So if we were to separate these into their own respective piecewise bounds, since x only applies from 0 to 3, we have the bounds of 0 to 3. Since x only applies from 0 and above, we have the bounds of 0 and above. Since negative x only applies in this piecewise function for 0 and below, we have the bounds 0 and negative 3. So we can solve for this piecewise function like this, like so. And also the antiderivative of negative x is just a negative version of the antiderivative for x. So if we solve for everything individually, we get 3 squared over 2 minus 0 over 2. And if we solve for this, we get 0 over 2 minus negative 3 squared over 2. And the negative is here as well, since the antiderivative is negative x squared over 2. What actually happens is we get a value of 9 over 2 here. And then the negatives cancel out. In this case, these negatives cancel out. And negative 3 squared is just 9 over 2. So 9 over 2 plus 9 over 2 is equal to 9 over 2 plus 9 over 2 is equal to 9. Booyah. What we also could have done is, since this function is symmetric, is only like very specifically in certain cases, but since this function is symmetric, if we solve for the integral from 0 to 3 in this case, basically the area from 0 to negative 3 would be the same. So if we just multiplied this area by 2x, then you'd get the area of both sides here. But that's just multiple different techniques I just showed you to solve for the piecewise function here. But as always, if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.